Okay, so before we talk about Hilbert transform, we have to see a little bit about continuous time Fourier transform. So I have split the discussion about the Hilbert transform into two parts. The first part consists about the discussion of the continuous time Fourier transform, and the second part discuss about the Hilbert transform. So first let us concentrate on our first part, so which is about continuous time Fourier transform. So for any signal x of t, continuous time Fourier transform is defined as x of j omega equal to integral minus infinity to infinity x of t into e power minus j omega t dt. So we call this equation as analysis equation, and from x of j omega you can get back the original signal x of t using this equation, which is given by 1 by 2 pi into integral minus infinity to infinity x of j omega t into e power j omega t dt. So let us take small examples to understand the concept of Fourier transform. So let me take the first example to be x of t equal to e power minus at into u of t. So here I assume that a is greater than 0, so that the curve of this signal will look something like this. So obviously, as the signal exists from 0 to infinity, the integral in the continuous time Fourier transform also exists from 0 to infinity into e power minus at into e power minus j omega t dt. So this we can easily simplify as 1 by a plus j omega. Similarly, if we take another example to be x of t equal to e power at into u of minus t. So here again we assume that a is greater than 0, so that the plot of the signal will look something like this. So for this signal, it is non-zero from minus infinity to 0. So and hence the corresponding Fourier transform, the integral limits will be from minus infinity to 0 e power at into e power minus j omega t dt. So this again will be easily simplified to 1 by a minus j omega. Now we'll take third example as what happens if I add the previous two signals, that is, now x of t is e power minus at u of t plus e power at into u of minus t. So this signal can be written as e power minus a mod t. So the plot of which will look something like this. So equation of this curve will be e power at, and the equation of this curve will be e power minus at. So if you find the Fourier transform of this signal, so it will look something like this. So integral minus infinity to 0 e power at into e power minus j omega t dt plus integral 0 to infinity e power minus at into e power minus j omega t dt. So after simplification, this will be equal to 1 by a minus j omega plus 1 by a plus j omega. So this easily simplifies to 2a by a squared plus omega. Okay, so that is an example of, we have taken 3 examples here. So next we move on to one more example. What happens if I subtract the 2 signals? So let me take that as fourth one. So that is x of t is equal to e power minus at u of t minus e power at into u of minus t. So if you look at its plot, it will look something like this. Okay, so e power minus at u of t corresponds to this curve, minus e power at u of t corresponds to this curve. So this will be minus 1, this will be 1, and the corresponding, this is t. So equation of this curve will be e power minus at, and the equation of this curve will be minus e power at. So again, if you look at the Fourier transform of this signal, so it will be like integral minus infinity to 0 e power at into e power minus j omega t dt plus integral 0 to infinity e power minus at into e power minus j omega t dt. So after simplification, this will be equal to minus 1 by a minus j omega plus 1 by a plus j omega. So this easily simplifies to minus 2j omega by a squared plus omega squared. Okay, so next we will take one more example, fifth example, where we take x of t to be equal to delta of t. So for this, the plot will look like this, which is familiar to us, and the strength of the Dirac delta is 1. So for this, my x of j omega will be equal to integral minus infinity to infinity delta of t into e power minus j omega t dt. So this will be equal to integral minus infinity to infinity delta of t dt, so which is equal to 1. So if you plot this graphically, how does that look? So Dirac delta will have 1 as the Fourier transform. This is 1. So this is my x of t, which is nothing but Dirac delta, and the corresponding Fourier transform is x of j omega. So next we move on to a simple example for inverse Fourier transform. So for example, if we are given that the Fourier transform of a signal is like this, it is minus w to plus w with an amplitude of 1, we are interested in finding its inverse Fourier transform or the time domain signal. So for this, the synthesis equation will give me right 1 by 2 pi integral minus w to plus w 1 into e power j omega t d omega. So this will be equal to 1 by 2 pi into e power j omega t by j omega, integral limits will be from minus w to plus w. So this gets easily simplified to sin wt by pi t. Sin wt by pi t. So the plot of which will look something like this. So amplitude will be w by pi, and these limits will be pi by w, 2 pi by w, minus pi by w, and minus 2 pi by w, and so on. Okay, right. So next we will take one more example, or we'll proceed. We will write the previous equation in a neat way. So that is, we have got sin wt by pi t will have a rectangle signal from minus w to plus w as the Fourier transform. So if you take this as x of t, so this will be our x of j omega. So those are the few examples for Fourier transform and inverse Fourier transform. So next we move on to some important properties of Fourier transform. So first one we call it as linearity property. So what does it say? So it says that if x1 of t has x1 of j omega as a Fourier transform, and x2 of t has x2 of j omega as the Fourier transform, then a x1 of t plus b x2 of t will have a x1 of j omega plus b x2 of j omega as the Fourier transform. So this is the linearity property. So we will take a small example. So if we want to find, let us say, the Fourier transform of the signal defined by x of t equal to e power minus 3 mod t plus delta of t. Let us say we want to find the Fourier transform of this signal. So what does linearity property says? So it says that you directly find the Fourier transform of individual signals and then add them. So what will be the Fourier transform of this signal? X of j omega will be equal to, so we have seen that e power minus a mod t will have 2a by a square plus omega square as the Fourier transform, and delta of t will have 1 as the Fourier transform. So this simplifies to 1 plus 6 by 9 plus omega square. So that is the Fourier transform of this signal. So here linearity property helps us. So next important property is shifting property, time shifting property. So what does it say? So time shifting property. So what does it say? So if x of t has x of j omega as the Fourier transform, then x of t minus t naught has x of j omega into e power minus j omega t naught as the Fourier transform. So if you take a small example, so we have seen that e power minus 3t into u of t will have 1 by 3 plus j omega as the Fourier transform. Now if you want to find the Fourier transform of e power minus 3 into t minus 3 into u of t minus 3, so then applying time shifting property, for us t naught is equal to 3, so obviously what do we get? So this is our x of j omega. It will be like this: 1 by 3 plus j omega into e power minus j omega into 3. Okay, so that's it. So it's an easy way of computing the Fourier transform of this signal. So if you directly evaluate, it will take little bit time. So to avoid that computation time, we use the properties. So properties are just shortcuts for the evaluation of the Fourier transform. So we'll take one more example. So one more example is, so for example I want to find the Fourier transform of delta of t plus 3. Delta of t plus 3. So for this, again the Fourier transform will be 1. Now t naught has become minus 3. So obviously 1, the Fourier transform delta of t plus 3 will be equal to 1 into e power plus j into 3 omega. The delta of t plus 3 will be plus 1 into e power j 3 omega. Right. So next important property which we will be seeing will be frequency shifting property. So what does it say? So if x of t has x of j omega as the Fourier transform, then e power j omega not t x of t has x of j omega minus omega naught as the Fourier transform. So note that here positive sign implies negative sign here. Similarly, we can show that e power minus j omega not t x of t has x of j into omega plus omega naught as the Fourier transform. So if it is minus, it will become plus. If it is plus, it will become minus. So for example, if I add these two, the linearity property will help us in showing that x of t into cos omega naught t will have 1 by 2 into x of j omega plus omega naught plus x of j omega minus omega naught as the Fourier transform. So how do we get that? If you add these two guys, we can apply linearity property. So x of t is common. So e power j omega naught t plus e power minus j omega naught t is 2 cos omega naught t. So that too I have sent this side. So obviously these two values will get added up. So that is the corresponding Fourier transform. So again here we will take a small example. If I want, for example, I have a signal like this, sine, let us say 100 pi t by pi t. So just now we have seen that sine wt by pi t will have a rectangle signal from minus w to plus w, where for us w is 100 pi. So this will be minus 100 pi to plus 100 pi with omega and amplitude is 1. Now if I want to find the Fourier transform of sine 100 pi t by pi t multiplied with cos of, let us say, 400 pi t. Okay, so if I want to find the Fourier transform of this signal, so what does it say according to this property? So for us x of t is this and omega naught is this. So corresponding Fourier transform, how does it look? So x of j omega plus omega naught means you shift the Fourier transform to the left by omega naught units. So x of j omega minus omega naught means shift the Fourier transform to the right by omega naught unit. So here we have omega naught to be 400 pi. So obviously the overall Fourier transform, how does it look? The whole spectrum shift to the right by 400 units and shift to the left by 400 units. So how does the plot look? So the whole plot will look something like this. So this part will be 300 pi and this will be 500 pi. Similarly on the negative frequency side also you have the same thing. So this will be minus (500 pi) and this will be minus 300 pi. So here amplitude has become half. So this is the Fourier transform of this signal. Is it okay? So it is the Fourier transform of this signal. Similarly, so for example, what happens if x of t equal to delta of t? Or else we'll see that later. So next we move on to next important property called differentiation in time domain property. Okay. So differentiation in time domain. So what does it say? It says that if x of t has x of j omega as the Fourier transform, then d by dt of x of t has j omega into x of j omega as the Fourier transform. So this is very useful property. So its use, let us see with an example. So for example, if I have a signal like this, a rectangle signal, let us say from minus t to plus t, whose amplitude is 1. So I want to find the Fourier transform of this signal. So one way of doing is direct method. One other way is using differentiation in time domain property. So let us see how do you use this differentiation in time domain property to find the Fourier transform of this signal. So if you have watched the video lecture about differentiation operation, so we have seen that wherever there is discontinuity, that discontinuity has to be replaced with a Dirac delta function, and the strength of Dirac delta will be equal to the amount of discontinuity. So obviously, so how does the d by dt of x of t of this signal look? So at minus t you have a discontinuity, and because the discontinuity is positive, you will have a positive Dirac delta at minus t of strength 1. Similarly, you have one more Dirac delta at t, but the strength of that Dirac delta is negative. So why is that? Because the signal is jumping from 1 to 0. So that corresponds to negative jump. So this is our d by dt of x of t. Now if I take the Fourier transform of d by dt of x of t, so how does that look? If I take the Fourier transform of d by dt of x of t, how does that look? So we can write, so let me write it in mathematical form. So we can write d by dt of x of t as delta of t plus capital T minus delta of t minus capital T. Correct? So we can write delta of x of d by dt of x of t as delta of t plus capital T minus delta of t minus capital T. So if you apply the Fourier transform on both sides, so what properties I have to use? So left hand side I have to use differentiation in time domain property, and on the right hand side I have to use time shifting property. So let us use that. So taking Fourier transform on both sides. So what do we get? So I get j omega into x of j omega will be equal to e power j omega t minus e power minus j omega t as the Fourier transform. So this, let us simplify this. This will be equal to j omega into x of j omega. So this will be equal to 2j into sine omega t. So j will get cancelled out. So we get x of j omega to be equal to 2 sine omega t by omega. So let us summarize this. So what is that? So x of t, which is a rectangle signal from minus w to plus minus capital T to plus capital T, will have a Fourier transform of 2 sine omega t by omega. Okay, so that's a good result. So let us try to remember this result. So this is the way how Fourier transform, the differentiation in time domain property will help us. So we'll take one more example. Let us take the Fourier transform of a triangle signal. So here now let me assume that my x of t is a triangle, let us say from minus t to minus t to plus t. Let us say amplitude is 1. So if you look at this equation of this line will be 1 plus t by capital T, and the equation of this line will be 1 minus t by capital T. So if you differentiate this once, how does that look? If you differentiate this once, how does the waveform look? So obviously from minus t to 0 it is 1 plus t by t. So if you differentiate that, you will get, so if you differentiate this, you will get 1 by t. Similarly from 0 to t it is 1 minus t by t. So if you differentiate that, you will get minus 1 by t. So one way is you can stop here and you can use time shifting properties, because we are already aware of Fourier transform of rectangle signal. But to make our life simple, let us differentiate this fellow one more time. Okay, so what will happen? So if I differentiate this signal has 3 discontinuities at minus t, 0 and t. So I will have the derivative of d by dt of x of t like this. Okay, so at minus t I have 1 Dirac delta of strength 1 by t, and at 0, because the signal is jumping in negative direction, I will have a negative Dirac delta of strength minus 2 by t. Similarly at t I will have a positive Dirac delta of strength 1 by t. So this fellow is, let us say, x double dash of t. So how do you write this mathematically? So we can write d square x of t by dt square as 1 by t, if I take it out, or else let me write fully, delta of t plus capital T minus 2 by t delta of t plus 1 by t into delta of t minus capital T. So let us check that out. So I have a Dirac delta at minus t of strength 1 by t, that is this fellow, and I have a Dirac delta at 0 of strength minus 2 by t, and that is this fellow, and another Dirac delta at t with strength 1 by t, and that is this fellow. So that is okay. Now if you apply Fourier transform again on both sides of this equation, what do we get? So taking Fourier transform on both sides, okay, so what do we get? So we'll get j, because I'm differentiating twice, I have to get j omega whole square into x of j omega, that will be equal to, here left hand side I have to apply differentiation in time domain property, right hand side I have to apply the time shifting property. So 1 by t into, for these two fellows 1 by t is common, so what happens, I'll get e power j omega t plus e power minus j omega t. Okay, so minus 2 by t into delta of t Fourier transform is 1. So let us simplify this. What will happen? So left hand side will become minus omega square into x of j omega, so that will be equal to 1 by t into, so if you look at this equation, 1 by t into this will be 2 cos omega t, so I will get 2 cos omega t, 2 cos omega t minus 2 by t. So what will happen to the right hand side? So this will be equal to, so for both the guys 2 by t is common, so I'll take minus 2 by t out, so this will be equal to minus 2 by t. So if I take minus 2 by t out, I will get 1 minus cos omega t. So what will happen now? So this will be equal, so right hand side will be same as minus omega square into x of j omega. So what happens, this minus will get cancelled out, so I'll get x of j omega to be equal to, see 1 minus cos omega t is 2 into 2 sine square omega t by 2 by omega square. So what will happen? So 1 minus cos theta is 2 sine square theta by 2. So for us theta is omega t, so obviously you will get this as the Fourier transform. So this simplifies to what? So let us write in a short nice form. So the Fourier transform of that triangle signal will be equal to how much? 2 into 2 is 4 sine square omega t by 2 by omega square. 4 sine square omega t by 2 by omega square. So next let us move on to another property, differentiation in frequency domain. Differentiation in frequency domain. So what does it say? What does it say? If a signal x of t has x of j omega as the Fourier transform, then tx of t will have j into d by d omega of x of j omega as the Fourier transform. Okay, so let us illustrate this with an example. So I will take, let us say x of t is e power minus at into u of t. So if you want to find the Fourier transform of t into x of t, okay, so that is the task. I want to find the Fourier transform of t into x of t. So we already know that e power minus at u of t will have 1 by a plus j omega as the Fourier transform. So obviously t into e power minus at u of t will have j into d by d omega of x of j omega. X of j omega is 1 by a plus j omega. So this will be equal to j into minus 1 by a plus j omega whole square into again j. Correct? So let us see it again. So j into d by d omega, so x of t is e power minus at u of t for us. So t into x of t will have j into d by omega of d by d omega of x of j omega. X of j omega is this for us. So if you substitute that, I will get j into d by d omega of this. This will be minus 1 by a plus j omega whole square into j. So that will be equal to, so j into j is minus 1 into minus 1 is plus 1. I will get to 1 by a plus j omega whole square. Okay, so finally what did we get? So we got t e power minus at u of t will have 1 by a plus j omega whole square as the Fourier transform. So let us extend this result. Like I want to find the Fourier transform of, let us say, t square into e power minus at u of t. Okay, so this can be written as t into e power minus at into u of t. So obviously this will be, we will have what as Fourier transform? J into d by d omega of. Correct. So what is the Fourier transform of this, which we have already got? That will be 1 by a plus j omega whole square. Correct. So that will be equal to again j into minus 2 by a plus j omega whole cube into again j. So that will be equal to, so j into j is minus 1 into minus 1 is plus 1. So this will be equal to 2 by a plus j omega whole cube. So you can proceed in the same way. So if you are interested, you can take it as homework. You try to prove that t power n into e power minus at u of t will have n factorial by a plus j omega whole power n plus 1 as the Fourier transform. So it's a good task. So it is nice if you can solve it. Okay, right. So next we move on to what is called duality property. Okay, so what does it say? So it says that if x of t has x of j omega as the Fourier transform, then x of jt has 2 pi into x of minus omega as the Fourier transform. Okay, so again let us illustrate this with an example. So what does it say? I have a signal x of t corresponding Fourier transform with x of j omega. Again, if you take the Fourier transform, what will happen? So if you take again the Fourier transform of x of t, you will get back the flipped version of your original signal as the Fourier transform. So let us illustrate this with an example. So for example, if I want to find the Fourier transform of x of t equal to 1 by 3 plus jt. Okay, so I am interested in finding the Fourier transform of 3 by 1 plus jt. Okay, so where should we start? We should start at, we know that e power minus 3t u of t will have 1 by 3 plus j omega as the Fourier transform. So if you take this fellow as x of t, the corresponding signal is this, and the corresponding Fourier transform is x of j omega. Now what should I do? If I replace omega with the t, what will I get? My x of jt. What is that I have done? I have replaced omega with t. So my x of jt will be 1 by 3 plus jt. So what will be the corresponding Fourier transform according to duality property? 2 pi into x of t. X of t is this, 2 pi into x of minus omega. Minus omega means what? Wherever there is t, replace with minus omega. So what will I get? So this will be equal to e power 3 omega into u of minus omega. So 1 by 3 plus jt will have 2 pi into e power 3 omega by u of minus omega. So we'll take one more example. So let us say I want to find the Fourier transform of x of t equal to, let us say, 1 by 1 plus t square. Okay, so again where should I start? I will take my x of t to be e power minus mod t. So for this we already know the Fourier transform to be how much? 2 by 1 plus omega square. So let me call this as x of j omega. Now if I replace omega with t, what will happen? X of jt will be equal to, x of jt will be equal to 2 by 1 plus t square. So 2 by 1 plus t square. So corresponding Fourier transform according to duality property. So 2 pi into x of minus omega. X of t is this, x of minus omega will be e power modulus of minus omega. So that will be equal to 2 pi into e power minus mod omega. So that is the Fourier transform of 2 by 1 plus t square. So if you want the Fourier transform of 1 by 1 plus t square, what happens? You multiply throughout with 1 by 2 or cancel out 2. So finally what do we get? So we get 1 by 1 plus t square will have pi into e power minus mod omega as the Fourier transform. Okay, so now let us take another example like x of t equal to 1 by pi t. Okay, so before we start finding the Fourier transform of 1 by pi t, let us find the Fourier transform of, let us say, h of t is equal to signum of t. H of t equal to signum of t. So why should we take the Fourier transform? Why should we know the Fourier transform of signum of t? You will know in a moment. So let us see how the signum of t looks. So we know that signum function will look something like this. So this is our h of t. So what will be d by dt of h of t equal to? So if you find d by dt of h of t, so what will happen? So if you look at that signal, wherever there is discontinuity, you have to replace with a Dirac delta. So what is the, because it is a positive jump, we have to replace with a positive Dirac delta with strength 2, because it is jumping from -1 to +1. So how does the plot of that guy look? So d square h of t by dt will look something like this. Okay, so it will look something like this. So this is same as what? 2 times delta of t. Okay, so that is same as 2 times delta of t. So if you take the Fourier transform on both sides, what do we get? So I will get j omega into, let us say, h of j omega. So that will be equal to 2, or from this we get h of j omega to be equal to 2 by j omega. So what does it mean? I have got that signum of t will have 2 by j omega as the Fourier transform. So if you take this guy as x of t, and if you take this fellow as x of j omega, then what do we get? X of jt will be equal to, so I am applying duality property now, 2 by jt. So this fellow will have 2 pi into signum of minus omega as the Fourier transform. Okay, so 2 pi into signum of minus omega as the Fourier transform. Okay, so if we take x of t to be signum of t, so that will have 2 by j omega as a Fourier transform. So if we replace omega with t, okay, you will get 2 by jt. So corresponding Fourier transform will be 2 pi into signum of minus omega. So signum of minus omega, so clearly signum function is an odd function. So I can replace signum of minus omega with minus signum of omega. So if we cancel out 2, what will I get? We cancel out 2 and multiply with j by pi. What will I get? So multiplying with j by pi t, j by pi, we get, so what do we get? If you multiply throughout, you will get 1 by pi t will have, so pi will get cancelled out, so j will remain, and we have seen that signum function is an odd function, so obviously you will get minus j into signum of omega. So multiplying with 1 by pi, we get 1 by pi t will have minus j into signum of omega. So 1 by pi t is a very important example. So our Hilbert transform of any signal x of t starts with 1 by pi t. So just before we end, we will see the definition of Hilbert transform. So we define the Hilbert transform of any signal x of t as x h of t is equal to x of t convolved with 1 by pi t. So if you convolve any signal x of t with 1 by pi t, you get what is called Hilbert transform of a signal. So we will stop here, and the continuation of the Hilbert transform we will see in the next lecture. Thank you.